Hello, this is Mr. Nadeau. Welcome to your first online presentation for AP Physics B. As I mentioned in class, this presentation supplements and elaborates on the reading, so you should read the text first and then come to this presentation. So if you haven't done the reading, you should stop the video. No, really, you should stop the video. Go do the reading and come back. Alright, so you're going to find that throughout this year, you're going to have these presentations for homework. Most classes, you would have these kind of PowerPoints during class time itself. But as I mentioned in class, AP Physics B is very problem-solving intensive. And I want to give you time in class to interact with me when you're working on problems. Because if I gave you a lot of problems to do at home, you want to have me there to help you out. But if we do problems in class together, I think you'll find you're going to get more comfortable with the problem-solving process, and you'll find over time that you'll get to be able to do problems on your own with ease. So this presentation is going to help us, give us more class time to work on more intense problems, to do demonstrations, to work on difficult conceptual ideas. Also, this is a powerful way of presenting information to you because you get the chance to actually view the presentation at your own pace. If you're feeling overwhelmed about the topic or what we're talking about, you can actually just stop the presentation, try to absorb what you can, rewind if you need to, and then continue. You couldn't do that in a regular classroom. If somebody raised their hand and said to a teacher that was giving a PowerPoint, hey, Mr. Blah, 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 could you stop the presentation because it's kind of overwhelming right now. The information is not really sinking in. Could you resume it in 15 minutes or so? That'd be great. Yeah, you can't really do that in a classroom. But the nice thing is when you have a presentation like this online, you can do just that. All right, so let's get started. The first presentation is going to be pretty laid back. I just want to give you a sense for what these will be like. So we're not going to talk about a whole lot today. But what we're going to discuss is the basics of motion. Because it turns out in physics we talk about motion a lot because it helps us explain what's going on with physics phenomenon. So you really have to understand how physicists look at motion. And so we're going to start with the basics of visualizing motion, how physicists actually look at motion. Because it turns out most people, when they think about motion, they don't really separate what different kinds of motion there are. So if you talk to somebody on the street and you point to a car that's speeding up and you say, hey, what is that car doing? They'll say, hey, it's moving. If you point to a car that's moving at a constant speed, so it's not getting faster or slower, and you say, hey, what's going on with that car? They'll tell you, hey, well, it's moving. But notice how by saying both those things are moving, you're not getting specific. In physics, we like to get specific. We like to say, hey, this object's speeding up, this object's moving at a constant speed. And so we want to make sure that you're comfortable with how physicists look at motion. So the first thing we're going to look at is how we visualize motion. And this visualization process is called a motion diagram. So first let's talk about how you make a motion diagram. The best way of thinking about a motion diagram is thinking about how film is made. It turns out a film strip made by a movie camera is really just a bunch of snapshots that are put together. And then when they're run in the movie theater, run through a projector, those snapshots pass by very quickly. So you might see 30 snapshots every second. And your brain can't really tell, because it's moving so quickly, that all of those snapshots are still photographs. And so your brain puts it together and it looks like the film is actually in motion. So what we do in physics is we take this idea of the film strip, the idea of different snapshots, and we look at a moving object with different frames. Now a frame is just a separate photograph. So you'll see we've got some film here of a car. The car is clearly, if you look at each frame, moving from left to right. And you'll see that we have a snapshot of the car during different points of its motion. you should know that each frame is equal intervals of time. So from this car location to the next car location, that's about 1/30th of a second if we have 30 frames per second. So the key thing, it's not important that you know it's 1/30th of a second, but the key thing is to realize that each snapshot is taken in intervals of time that are equal. So each snapshot that you see here is taken in equal intervals of time, every, say, 1/30th of a second. You'll see that in equal intervals of time, this car is moving again across from left to right. Now, in a motion diagram, we separate those frames out, and we look at the car's motion in that way. We kind of stack them on top of each other. So you'll see that the car is here, then it's here, then it's here, then it's here. Each snapshot of the car is telling you about its location in equal intervals of time. So from this first snapshot of the car to the next snapshot of the car, 1/30th of a second passed by. And then from this snapshot to the next snapshot, 1/30th of a second passed by. So notice how the key thing about a motion diagram is we keep the interval of time between snapshots the same. And again, this is what we call a motion diagram. Now, some motion diagrams are pretty simple. If you look at a stationary object, if you took snapshots of an object that's not moving, you would notice that the picture looks exactly the same every single time. So as a result, the motion diagram, well, it's not very interesting. A stationary ball on the ground would just look like this because it's not moving. So if we take snapshots every equal interval of time, you would just see the ball in the same location. Now, if we look at an object that's moving at a constant speed instead, so if you look at the skateboarder on the bottom here, the skateboarder is moving from left to right at a constant speed. You'll see that we take a snapshot of the skateboarder in equal intervals of time, and notice that the distance that skateboarder covers is the same. And you'll find out later on that tells us that the skateboarder is moving at a constant speed because it's covering equal distances in equal periods of time. Now, if we want to talk about an object speeding up or slowing down, let's look at a speeding up scenario. So we have a sprinter that is doing a 100-meter dash. So they start at the starting block, and then they get faster and faster. Now notice if we take a snapshot of the sprinter in equal intervals of time, you'll see that she's covering more and more distance in those intervals of time. So if the first snapshot happens here, the next snapshot happens maybe 1/30th of a second later. Notice how she covers a small distance. And then the next 1/30th of a second, she's covering more distance. Then the next 1/30th of a second, she's covering even more distance. So notice how if we take a snapshot, equal intervals of time, she's covering more and more distance. She's speeding up. Now for an object slowing down, here's a car that's slowing down as it approaches a red light. Notice how the first snapshot, the car is at this location. The next snapshot, notice how the car covered this distance. And then the next snapshot, the car covered this distance. Notice how the distance is less. That's because it's slowing down. So it covers less distance in equal periods of time. And so a motion diagram of an object slowing down looks like that. Now we can also look at complex motion that's two-dimensional. Now when I say two-dimensional, that phrase indicates that we look at both a vertical and a horizontal. Now vertical, remember, is up and down. Horizontal is side to side. You can kind of remember it this way. Horizontal is like the horizon, which is where the sun sets or rises. And if you look across, say, the ocean, you would notice that the horizon is side to side. So horizontal means side to side, vertical means up and down. So you'll see we can actually look at complex motion with motion diagrams. We have a basketball. And this basketball, we're taking pictures of it, snapshots of it, in equal periods of time. Oops. And you'll see that there are two things happening. One is moving horizontally in this direction, And notice how it really is horizontally kind of covering equal distances in equal periods of time. And also, there's a vertical thing happening. If you look at it vertically, notice how it's rising up, and then it gets to the top of its motion at this location, and then it falls down. So this motion diagram is showing us two things. It's showing us the horizontal, and it's showing us the vertical motion. Now, luckily for me, we don't draw the objects as we see them. If you've ever seen my artistry, or the lack thereof, it's pretty awful. So this is a huge godsend for me. The nice thing is in physics, we don't actually draw the objects out. We use a dot to keep track of what the object's doing. We call this single point, this dot, a particle. So it's almost like we compressed the object down into one location, one little dot, and that's what we call the particle. Now, a particle has no size, no shape, no top, bottom, front, or back. It's just a dimensionless particle. So below we have the motion diagram of a car stopping using the particle model. Now, here's the car stopping that we saw before. Notice how we took that car and we condensed it down into a dot, and we're actually looking at the car slowing down. It's covering less and less distance in equal periods of time. Also notice how we've numbered the dots. So we have 0, 1, 2, 3, 4. Now, those numbers are indicating the sequence of the frames. So this is the first snapshot, the 0. The 1 is the next snapshot, 2 is the next snapshot, and so on. 3 is the next snapshot, 4 is the last snapshot. That just gives you a sense for the sequence, how it happened chronologically. So here's another motion diagram. This is an object that is moving upward, because notice how it starts at 0, then 1, then 2, then 3, then 4. And notice how these dots have different spacings between them. Question for you. What does that mean about the motion of the object if the dots are getting further and further apart? So take a moment to think about it. Yep, it means that the object is speeding up. So this rocket is getting faster and faster, so it's covering more and more distance in equal periods of time, and that's represented by those dots getting further and further apart. Notice how the rocket is moving vertically here, so we demonstrate that with the dots being up and down. So that's motion diagrams for you. We're going to use these motion diagrams to understand what happens with different types of motion. Just so you know, as a preview, the next time you look at a presentation, we'll be talking about the foundation of describing motion. We'll be looking at things like displacement, vectors, and scalars. So that will be on an upcoming presentation. All right, I'll see you tomorrow.